Chapter 6 FIR Filter Design. This chapter describes a technique that can be used to obtain the coefficients of FIR filters. Also, in this chapter, the design of FIR filters with equi-repel optimum using the Parks-McClellan algorithm is explained. After reading this chapter, you will be able to determine whether the phase response of a filter is linear based on an impulse response. Design an FIR filter using the window method. Identify and use the optimization criteria used in the design of FIR filters with the same repel. Determine the characteristics of a filter in terms of passband, stopband frequencies and levels, and relative passband, stopband repel. State the importance of controlling the results of the Parks-McClellan, also called Remez exchange algorithm, and if the results are not converged, make the necessary corrections and continue the design. The next topic, linear phase. Linear phase filters prevent signal waveform distortion. This feature is necessary in some applications such as video, data transfer, and music. In general, delay causes phase shifts that are proportional to frequency, that is linear phase. We can add or subtract delays to this system without affecting its linear phase characteristics. In addition to the delay, there are two other conditions that can cause the phase response to be constant. The first condition is that the frequency response h of omega is completely real. So there is no phase. It's a horizontal line for all omega. In this case, the phase is equal to 0, still linear. From the Fourier transform properties, it can be said that if h of omega is true, the impulse response must be even. Similarly, if the frequency response is completely imaginary, with constant phase plus minus pi over 2, then the impulse response must be odd. Therefore, a condition for a system to have a linear phase is that the impulse response should have an even or odd symmetry with respect to a point, maybe axis, maybe point sample. Now, group and phase delay. When describing systems with an approximately linear phase response, it is often appropriate to specify how far they deviate from the ideal state, that is, with a linear phase response. Okay? When a signal passes through a filter, its amplitude and maybe or phase changes. The nature and size of the signal change depends on the amplitude and phase characteristics of the filter. The phase delay or group delay of a filter provides a useful measure of how well the filter changes the phase characteristics of the signal. If we consider a signal that contains multiple frequency components, such as a speech waveform or a modulated signal, the phase delay of the filter is the amount of time delay that each frequency component of the signal endures in passing through the filter. On the other hand, average group delay is the time delay that the composite signal endures. Mathematically, phase delay is the negative phase angle divided by frequency, while group delay is the negative derivative of phase with respect to frequency. In mathematical form, here you see phase delay minus theta of omega over omega, and group delay minus d theta of omega over d omega. Right. The idea of phase delay is more useful for analyzing broadband signals which cover the entire frequency range from -pi up to pi. Similarly, group delay is widely used in the investigation of systems with narrowband input signals. For example, let x of n be S of n times e to the power of j omega 0 n, where S of n is a signal with very slow time variations. In this case, the system output will have the following behavior. Y of n is approximately equal to apps of h of e to the power of j omega times S of n minus group delay of omega 0 times e to the power of j omega naught times n minus phase delay of omega 0. The above equation shows that Tp of omega 0 imposes a phase shift on the carrier e to the power of j omega 0, while the group delay is a delay imposed to the envelope of the signal S of n. It should be noted that this equation is only valid for integer values of Tg of omega 0. Okay. A filter with a nonlinear phase characteristic will cause a phase distortion in the signal that passes through the filter. The reason is that each of the frequency components in the signal is delayed by an amount that is disproportionate to the frequency. As a result, their harmonic relations will be changed. In many applications, such as music, data transmission, video, and biomedical science, such distortion is undesirable. In such applications, filters with linear phase characteristics can be used on the frequency bands of interest to avoid phase distortion. A filter has a linear phase response if its phase response satisfies one of the following relations. Theta of omega is equal to minus alpha times omega, or theta of omega is equal to beta minus alpha times omega, where alpha and beta are fixed values. Beta is normally pi over 2 or minus pi over 2. If a filter satisfies the condition given in the first equation above, it will have both constant group and phase delays. In order to satisfy this condition, the impulse response of the filter must have positive symmetry. In this case, the phase response is only a function of the length of the filter. What does it mean? It means that we will have h of n is equal to h of capital N minus n minus 1. N is equal to 0, 1 up to half of n, and the same if it's odd or even, okay? And alpha is equal to n minus 1 over 2. Now, when only the condition given in the second equation above is satisfied, the filter will have only one fixed group delay. In this case, the impulse response of the filter has negative symmetry, meaning that h of n will be equal to minus h of capital N minus n minus 1, where alpha is equal to half n minus 1 and beta pi over 2. Right. FIR filters with linear phase have a unique set of properties that influence how they are designed and implemented. Now, the next topic, types of symmetry in FIR field. FIR filters can have 4 different types of symmetry, which are discussed and described below. It should be noted that in the following discussions, the filter degree of n is equal to capital M plus 1. So, M means the maximum delay in the impulse response of the filter. You need to remember it. You'll later need them in later discussion. Type 1 symmetry. M even and having even symmetry. Type 2. M odd and even symmetry. Type 3. M even but having odd symmetry. Type 4. M odd and odd symmetry. So 4 types of symmetry for FIR to have linear phase. Now we are going to see how. Type 1 symmetry. In this case, the filter degree is odd. We will explain how it works by citing an example. Let n be equal to 5, then m 4. So h1 of n will be b0 delta of n plus b1 delta n minus 1 plus b2 delta n minus 2 plus b1 delta n minus 3 plus b0 delta n minus 4. Now, have a deep look here. b0, b1, b2, b1, b0. Okay? Can you find the symmetry? Again, repeating b0, b1, and in the middle, b2. Okay? This is type 1. Its frequency response will be simplified as follows, which shows that the phase of the filter is linear. Okay. H1 of omega is equal to b0 plus b1 e to the power of minus j omega, b2 minus j2 omega, b1 minus j3 omega, b0 minus j4 omega. To speed up, I'll pronounce them right here. Okay. So it will lead to having e to the power of minus j2 omega, okay, taking factors, half of the most right-hand side parameter. Minus 4, remember, divided by 2 will be minus 2. Okay, so e to the power of minus j2 omega, which will lead to have b0 times e to the power of plus j2 omega, okay, plus b0 e to the power of minus j2 omega related to the last term. Now, the second term, b1 e to the power of j omega plus b1 e to the power of minus j omega. Minus 1 minus 2 will be minus 3. Leaving b2 alone here without any terms of e to the power of j omega. Okay? Now the third line, again, we will have 2 b0 cosine of 2 omega inside the bracket plus 2 b1 cosine of omega plus b2. Finally, e to the power of minus j2 omega times an amplitude. So amplitude is an even function, here you see, and phase is odd, and phase is also linear. In the general case, for even M and even symmetry, it was an example we find in general form. H1 of n will be b m over 2 plus summation k from 0 up to m over 2 minus 1 bk times delta n minus k plus delta n minus m plus k. So h1 of omega will be e to the power of minus j m over 2 times omega multiplied by b m over 2 plus summation k from 0 up to m over 2 minus 1, 2 times bk times cosine of m over 2 minus k multiplied by omega, which will lead to the third line without reading it out. Okay? Type 2 symmetry. In this case, the filter degree is even. We described an example of it as follows. If n is equal to 6 and m will be definitely 5, the impulse response of the FIR filter will have the second type of symmetry as follows. Here you see H2 of n will be B0, B1, B2, B2, B1, B0. The first one had only one term of B2, but here you see completely B0, B1, B2, B2, B1, B0 with corresponding delta, whose frequency response is simplified as follows and shows that again the phase of the filter is linear. H2 of omega will be e to the power of minus j 2.5 omega apps of H2 of omega. Here you see what stands for apps, again terms of cosine, and a linear phase. Okay? In general, for odd m and even symmetry, we have H2 of n is equal to sigma k from 0 up to m minus 1 over 2 bk times delta n minus k plus delta n minus capital M minus k. Okay, I won't read out H2 of omega. Here you see any details related to the term H2 of omega. Okay? Having linear phase and an amplitude which is even. Anyhow, note that H2 of e to the power of j pi is equal to 0 for the second type of filter. But the first type wasn't H1 of e to the power of j pi wasn't equal to 0. So please remember it. Later we will say what it means. Type 3. In this case, the filter degree is odd. Here we examine an example. Let n be equal to 7, m6. The impulse response of the FIR filter will have symmetry of the third type and will be as follows. Just reading out the coefficients B0, B1, B2. Okay? Having a 0 here for delta n minus 3, and again, repeating from the first, B0, B1, B2, 0, minus B2, minus B1, minus B0. Okay? Its frequency response is simplified as follows and shows that the phase of the filter is linear. H3 will lead to having such relation. E to the power of j times pi over 2 minus 3 omega multiplied by an amplitude showing exact details here. We don't have time to read out everything. In the general case, for even m and odd symmetry, H3 will be equal to k from 0 up to m over 2 minus 1 bk times delta n minus k minus delta n minus capital M plus k. And here you see frequency response. having linear phase and amplitude. It should be noted that for the third type of FIR filter, the following relation holds. The frequency response for both 0 and pi is equal to 0, meaning that it won't let the low frequency 0 and high frequency pi pass. So again, what's the usage? We will later see. Now, finishing up with the fourth type. In this case, the filter degree is even. Here we examine an example. Let n be equal to 6 and m 5. The impulse response of FIR filter will have symmetry of the fourth type and will be as follows. Here again, B0, B1, B2, having no 0, immediately minus B2, okay? B0, B1, B2, minus B2, minus B1, minus B0. Its frequency response is simplified as follows and shows that the phase of the filter is linear. Okay, H4 will be here the last line, e to the power of j times pi over 2 minus 2.5 omega times an amplitude, being shown in inside bracket, okay, curly bracket. Okay, in the general case for odd M and odd symmetry, we have H4 will be summation k from 0 up to m minus 1 over 2 bk times delta n minus k minus delta n minus capital M plus k, and having frequency response without reading it out. You see every details here related to H4. Note that for the fourth type of filter, we will have H4 of e to the power of j0 will be 0. Okay, preventing passing 0 frequency. Now, so having a conclusion, we mentioned 4 types of FIR leading to linear phase. Now, important conclusion. The second, third, and fourth types of symmetry are not suitable for high-pass filtering because their frequency responses are equal to 0 for omega being equal to pi. Okay? Symmetry of the third and fourth types are also not suitable for use in low-pass filters because their frequency response is equal to 0 at 0 frequency. Now, due to the application of 90-degree phase, the third and fourth symmetries are more suitable for the design of derivatives and Hilbert transform. Okay. Now take home 6.1. Write a program in Python that simulates the 4 types of symmetries mentioned and plots the amplitude and phase of their frequency responses.